So this is section 4.2. We're going to concentrate on isosceles and equilateral triangles. So we have our first theorem, the base angles theorem, and it begins with if two sides of a triangle are congruent. So you will either be told or shown that two sides are congruent. So you will be given AB is congruent to segment BC. And then the angles opposite them are congruent. So we need to understand what they mean by opposite them. So opposite is going to be across from. So when you go across from the side AB, you're going to point at angle C. And when you go across from side BC, you're going to be pointing at angle A. So our conclusion will be that angle C will be congruent to angle A. They're the angles opposite our congruent sides. So our next theorem is the converse of our base angles theorem. And remember, converse just switches the order. So this time we're going to begin with the two angles of the triangle congruent. So we're going to begin with the congruent angles. So you will be given or shown. So here we're going to have angle A congruent to angle C. And our conclusion is that the sides opposite them are congruent. So there's that phrase again, opposite them. So if you go opposite angle A, you'd be looking at the side BC. And if you go opposite angle C, you'd be looking at the side AB. So our conclusion would be that our side BC is congruent to our side AB. Keep in mind that an equilateral triangle is a special isosceles triangle. So our equilateral triangle is when all of our sides are the same. And if we apply the base angles theorem to that, opposite each of our congruent sides is a congruent angle. And when all of the angles are the same, it is equiangular. And if we go with the converse, we start out with the equiangular and we end up with the equilateral. So you cannot have equilateral without equiangular, and you can't have equiangular without equilateral. So we're going to apply these theorems and corollaries and find missing values within triangles. So here's our first question. And when you get to these, pay close attention to what's being identified as congruent. So we have three congruent sides. This gives us a equilateral triangle. And according to our corollary, equilateral is going to be equiangular, which means that we're going to get three congruent angles. So our x value measures the angle, and all of our angles are congruent, so they are all 3x degrees. So from here, we have to use some previous information, and we're going to use that triangle sum theorem. So the sum of our interior angles of any given triangle is 180. So we have three angles of 3x that are going to have to make 180. So 9x equals 180, and our x value is 20. In our next example, our congruent items are two angles. So we have two congruent angles, And when we have this, we can use the converse of our base angles theorem and get that the angles opposite, or the sides opposite them, are congruent. So we can get two congruent sides. So our two congruent angles are going to give us two congruent sides. So we go to the opposite sides, which just happen to be the ones with expressions, and these are going to be congruent as well. So remember that congruent means that they have equal measures. So we're going to take the 6x minus 4 and set it equal to the 20. So our 6x is going to equal 24, and x equals 4. So if you're given congruent angles, we can get congruent sides using the converse of the base angles theorem. Our third one looks a little complicated, but if you look very closely, this is the first time we have a value of y, but it's not a whole side. It's actually just measuring this one piece of a side, and it has these double marks on it. If you remember, slash marks indicate things with the same measure. So when we find another piece with that double marking on it, it's the value of 4. So our value of y is the same as 4. We also have some single markings on here, so that means everything with a single marking is going to be 3. So when I look at my information and try to find the value of x, we have to be careful because our x is an angle measure. So I'm looking to get congruent angles. In order to get congruent angles, I need congruent sides. So if we look at the whole sides of these triangles and do a bit of segment addition, so if we apply our segment addition postulate and add those sides, 3 plus 4 will make this side 7. We already have a 7 on the other one. On our third side, we once again end up with 3 plus 4 to get 7. So when we look, we actually end up with 3 congruent sides. So we're going to get 3 congruent angles. So we have our x, we're going to have another x, and this final corner will also be x. And once again, we can use the triangle sum theorem. And we're going to have our x plus our x plus x to be 180. So this time it's 3x equals 180, and x is equal to 60. Now our next problem has a triangle in a triangle, and I highly recommend when you get a complicated picture like this that you redraw the information. So we're going to start with the larger outside triangle. It has a vertex angle of 50 degrees. It has double slash marks on the left and the right. And then when we get down here to our angle measure, it has multiple pieces. So we're going to use the angle addition postulate, because anytime we have parts, we can add to get the whole. So we're going to take that 2x and add the 3y to get the measure of that whole angle. When we look at the smaller triangle that's inside of it, it has a 90-degree angle. It has a single slash mark on the left and the right, and it has a 3y degrees for the angle measure. So when we look at this situation, we have congruent sides, and we can get congruent angles using our base angles theorem. So because of the congruent sides, we're going to get congruent angles. So that means that in the larger triangle, the other side is also 2x plus 3y. And in our smaller triangle, our 3y is going to be on the left and the right side. So we're going to use the base angles theorem for both of those. We can only solve an equation with a single variable. So we're actually going to deal with the smaller triangle first and then the larger triangle second. So in our smaller triangle, now that we have a value for each of our angle measures, we're going to do the triangle sum theorem. So we have a 90-degree angle, a 3y, and a 3y to make the 180. So our 6y plus 90 is going to be 180. So 6y equals 90, and y equals 15. Now that we know the value of y, we can go back to the other triangle, and we're going to start with a little substitution. Because now that we know that y is 15, 3 times 15 is going to make 45. So we have 2y plus 45 for those angle measures. And now that we have a value for each of the 3 angle measures, we're going to do the triangle sum theorem for this triangle as well. So in this triangle, our vertex angle is 50 degrees. Our left angle is 2x plus 45 degrees. And our right bottom angle is also 2x plus 45 degrees to equal 180. Combine your like terms, 2x plus 140 equals 180. So 2x equals 40 and x equals 20. So we want to deal with the 2 triangles that have sets of congruent sides. So we can use our base angles theorem. So for this problem, we have our triangle on the bottom left that has 2 sides marked the same. It has the left angle identified as 4x minus 10, and it has the right angle identified as 2x plus 12. And then we also have the smaller triangle that is above and to the right of that. It also has 2 congruent sides, and its vertex angle is 4y degrees. So when we look, once again, we have congruent sides, and once again, we can use our base angles theorem. So opposite those congruent sides, we get a set of congruent angles. So each of those base angles are congruent, and that's true for both of our sets of triangles. So when we look at our information, my triangle with the y doesn't have enough information to solve anything yet. So we're going to start with the triangle with the x. We're actually going to use that base angles theorem. So they are congruent, so they're going to be equal in measure. And we have 2 different calculations for the same measure, so we set those calculations equal. The 4x minus 10 and the 2x plus 12 are 2 calculations for the same measurement. We're going to subtract the 2x and get 2x minus 10 equals 12. We're going to add the 10 to get 2x equals 22, and divide by 2 to get x equals 11. So we're going to do several things in order to get back to finding the value of angle y. So it makes sense that we need to find our value of x to find the value of y. So we're going to start out with a bit of substitution. So I'm actually going to put in the 11. 2 times 11 plus 12 is 34. And our 4x minus 10 is also 34. Since my two triangles are connected, I'm going to go ahead and do the triangle sum theorem for triangle 1. So this is my first triangle. So that's going to be a triangle sum of 180, and I have an angle of 34 and an angle of 34, and I get 112 degrees. And then if we look very closely, we see that our two triangles have a common side. So this makes a linear pair on that side. So now we can use the linear pair postulate and our definition of supplementary in order to find our missing angle beside the 112. So linear pair gives us supplementary angles. Supplementary has a sum of 180. 180 minus 112 gives us 68 degrees. And so we have a 68-degree angle in our triangle. And because of our base angles theorem, there are actually two 68-degree angles in this triangle. And now that we have a measurement in all three of the angles, we can now go to our second triangle and do our triangle sum theorem for the triangle 2. So 68 plus 68 plus 4y will equal 180. So this is 136 plus 4y equals 180. 4y is going to equal 44, and our y is equal to 11. And our last example, I'm actually not going to redraw the triangles. So I have two triangles here. One triangle has y values, one triangle has x, and because I have more information with the top triangle, I'm going to start there. Because we have two congruent sides, we're going to get congruent angles using the base angles theorem. So my 7y minus 3 and 3y plus 13 are a set of base angles, so they're going to be equal. I'm going to set them equal. 7y minus 3 equals 3y plus 13. So that's going to be 4y minus 3 equals 13. 4y equals 16, and y is equal to 4. So now when I go to the second triangle, I have to be careful because there's not as much information. So I'm once again going to apply the base angles theorem here as well. So opposite my congruent sides, I get congruent angles. So that means I have a 2x plus 3 in this angle as well. Now I can't do like I did in the previous question because I don't have two different calculations for the same measurement. I'm repeating a calculation. So what we are going to have to do is we're going to go back to the first triangle because it turns out that we end up with a set of vertical angles. And we can use the vertical angles theorem in order to figure out another angle measure in triangle 2. So when we go back to the first triangle, we're going to go back and do the substitution. So 3 times 4 plus 13 is 25. So we get a 25-degree angle. And if you do 7 times 4 minus 3, you also get 25. And then we're going to do the triangle sum theorem for this triangle. So the triangle sum is 180, and we have a 25-degree angle and a 25-degree angle, and we end up getting 130 degrees. So now if we apply the vertical angles theorem, we get a 130-degree angle in the other triangle as well. And now we can once again do the triangle sum theorem. So in this bottom triangle, we have the 130-degree angle, the 2x plus 3 from the left, and the 2x plus 3 from the right to get our triangle sum of 180. So that's 4x plus 136 equals 180. So our 4x equals 44, and x equals 11.